Good morning, CC sir.
Good morning, sir.
Shall we start?
Yeah, we can start. I'll turn on my video.
Okay, sir. Up to the time being, you can share your screen.
Okay, fine.
Right now, I am starting the sessions. Good morning, one and all. Now, this is Dr. Ram Kumar Kars, Assistant Professor, EC Department and IT Researcher. Now, I would like to welcome you all in the 4-day first session on 1-week webinar on recent trends in signal processing and communication. I would like to extend my deepest gratitude to our honored speaker, Dr. CC Kalita, data scientist, our most arms of tech here. Before starting the talk, I would like to give a brief introduction about our respected speaker, sir. Sisir Kalita did his MTech from Tezpur University in 2012 and a PhD in pathological speech signal processing from the Department of EEE IIT Guwahati in 2019. Currently, he is working as a data scientist leading a speech group at Arms of Tech Air, where he is involved in developing various voice tech solutions such as speech to text, voice ID, and speech analytics for contact centers. He has published 17 research articles in peer-reviewed journals and conferences. His team received Samsung Innovation Award 2015 for developing a prototype to detect hypernasalities in pathological speech. He also received several travel fellowships such as DST Young Scientist Travel Fellowship, Microsoft Research India International Speech Communication Association student grant for attending international conferences. His area of research are pathology, speech processing, speech analytics, and acoustic phonetics. Sir, now it's over to you. Kindly, I request you to start the session.
Okay, thank you. Thank you. I'll share the screen first. Can I turn off my video? Screen is visible, sir. Sir, screen is visible.
Yeah, it is visible now. You can start the session.
Okay, thank you. Thank you. A very good morning to everyone. Thank you for the nice talk, Dr. Ram Kumar. I'd like to thank the organizer committee, especially Ram Kumar sir, for from NITCL sir for inviting me to deliver a talk in this webinar. And it is my great honor and pleasure to be part of this event. So here actually I'll talk about this hypernasality in cleft lip and palate, acoustic cues and modeling. And this talk actually, whatever I'm going to discuss, these are some research work related to pathological speech analysis, which my friend and I did during my PhD work. in IIT Guwahati under the supervision of Professor S.R. Prasanna and Professor S. Dhandapat. While doing this research, we created our own database with the collaboration of Professor Puspavati. She is currently Director of All India Institute of Speech and Hearing, and Professor Aziz K. Abraham, both are from All India Institute of Speech and Hearing, Mysuru. And we work in different cleft lip and palate speech dimension. Then this is my brief outline of the talk. Here, first, I'll talk about what exactly cleft lip and palate problem and what are the problems, speech disorder associated with this kind of congenital disorder. Then among different kind of speech disorder which are associated with the cleft lip and palate speech, I will only consider one particular kind of speech disorder which is called a hypernasality. And I'll talk about what hypernasality is. And we'll see what is the causes and what are the acoustic cues related to this. And what are the acoustic cues are defined for that to do the assessment. Then a detailed discussion, I'll make a few attempts, whatever we have made regarding the system development point of view that I'm going to discuss. But while doing this research work, since we found that no cleft lip and palate database is available all over the world, actually. One database is there, but that database is not publicly accessible. So we created our own database, and starting from that database recording to the model development, all the things we have done in our team in IIT Guwahati. And therefore, we develop one database, and we'll show what is the importance of clinical expert in this kind of data preparation and carrying out the research work. Then, then I'll talk about what are the acoustic cues are related to the hypernasality and how we can model the hypernasality. That I'll talk about. Then, coming to the cleft lip and palate. Pellet. This is a bone disorder, actually, which is called a congenital malfunction of craniofacial region. Craniofacial means this orificial region, and it was found that according to the World Health Organization, it occurs in approximately 1 in every 700 live births in worldwide. And we can see in India also our number of cases are more. Then these individuals with cleft lip and palate have different associated problems. Such as we can see that feeding problem they may have, then speech problem they may have, and hearing, and all together, since that he may be isolated, and then those socio-psychological some issues may happen. So that's why a multidimensional team, like team, maybe doctors, psychologists, clinicians, and different experts is required to treat this kind of children. Then here you can see in the right figure, there are experts have divided different kind of pathology, different kind of cleft lip and palate based on the where the cleft is occur and the position. We can see there are different kind of, like whether it is combined. Combined means whether it is there may be cleft in the lip or cleft in the palate. So this is called a combined. If cleft is there in lip also and palate also, this is called a combined. And sometimes it may be isolated. There may be only cleft palate or cleft lip. Then whether it is unilateral, that means whether it occurs both the sides of the nose or one side of the nose. That depends on that one. Then whether it is complete. In some of the cases, like for example, if you see the right figure, the top leftmost figure, then you can see this lip. In the lip, it is actually not completed. That cleft is not completed, so it is a incomplete kind of cleft. And this unilateral incomplete cleft lip. This is not a severe condition actually, but if it is like in the rightmost bottom, that where bilateral complete lip and palate is there. So at that time, this is a very severe condition. And generally, at the age of 1 year, it is suggested that it is at the age of 1 year, the first surgery should be done. But in India, that is not happen some of the time. So they associate some of the other problems like speech problems. Then to evaluate their speech, since I'll talk about only regarding the speech, then for the speech case, to evaluate their speech language pathologists are required for the diagnosis or evaluation purpose. But the problem in this case is that they are required very long-term therapy. That children with their parents, they need to stay with their maybe near to that place, near to the clinic, and they need to repeated visit needs to be done in that place. And it may take maybe 3 years, 4 years, or depends on what the severity is. Now, what are the speech? Since we are talking about the speech-related problems, so what are the speech disorders associated with the cleft lip and palate speech? Pellet. Now, there are different kind of speech disorder exist. If we consider any kind of speech pathology, there are a set of speech disorders are associated. And in case of cleft lip and palate speech also, there will be different speech disorders are associated. But for cleft lip and palate speech condition, hypernasality, nasal air emission, and articulation disorder, these three are the main category of the speech disorders. So among these three or four categories of the speech disorder, I'll only talk about this hypernasality speech disorder. So hypernasality is abnormal nasal resonance in case of voice oral sound. When we speak, generally, while I am speaking now, so at that time, what happened when I speak oral sounds? So I'll talk about what the oral sound is while discussing the how normal human speech production system works. So at that time, our phlegm should contact with one wall is there backside called posterior pharyngeal wall. But what happened due to the hypernasal speech? Actually, that contact didn't happen, and this oronasal coupling occur. Due to that, abnormal resonance occur in your in the oral sound production. So I'll play sounds from the normal speech, a normal speaker, and from the individuals with cleft lip and palate. First, I will play that cleft lip and palate. So maybe I need to remove my headphone. Are you listening that? Okay. So by listening this speech, it is a very severe hypernasal speech. So you can't actually say what exactly that person is speaking. So I'll play the normal one. So that actually that children is that person is speaking the kage kalu kappu. This is a Kannada sentence. Actually, since we did all the work and we collected the database from that institute, All India Institute of Speech and Hearing. So we did in the Kannada language. Then we can see here that all the speech is totally nasalized. Then coming to another problem, which is called nasal air emission. So this is the abrupt nasal emission happen during the production of the pressure consonant. Pressure consonant means stops or fricatives or affricates. So during the production of this kind of sounds, this nasal air emission problem happen for the cleft lip and palate children. So I'll play the first normal. Maybe I can play. Kaka. So that children is saying kaka. 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 You can listen like before producing the ka, there is abrupt sudden release of some kind of noise actually. So what exactly happening when we need to produce ka sound? We need to make constriction in the vocal tract. and then we suddenly release. That's why we get some abrupt energy release in the production of the ka. But what happens, since there is some problem in the phalanx with the posterior pharyngeal word, that gap is very small. That is not completely closed. That is, some constriction is there. That's why when we release that ka airflow, some of the airflow is released through the nasal cavity also. That's why you are listening this na sound, uh, na sound while producing the ka sound. So this is called a nasal air emission. Then articulation disorders. So what happened, since they have the problem in the vocal tract or sometimes in the larynx also, so the production of the stop consonants, fricatives and affricates, they may have the problem. Maybe I'll play one sound. So it's the same kaka sound. So you can see that ka is replaced actually. Ka is totally deleted. Actually, ka is replaced by one kind of phonemes which is called the glottal stop. So since this glottal stop is not present in most of the Indian languages, so it is difficult for us to perceive that sound. Because some of the language in our northeastern area have this glottal stop sound. But generally, most of the Indian languages don't have this glottal stop sound. But what these cleft palate children do, they try to compensate, since they can't produce the ka sound. They try to compensate with this kind of sound, which are more easier to them to produce those kind of sounds. Then coming to the voice disorder. Actually, these three, hypernasality, nasal emission, and articulation disorder, these are more associated with the cleft lip and palate children. But voice disorder is secondary to those problems. So because due to those articulation maybe problem, they may have this voice disorder, or sometimes they may have some kind of problem in their glottis. So due to that also they may have some kind of voice disorder. So, but in our database, actually, we didn't find any kind of voice disorder children which are cleft lip and palate individuals with voice disorder. That's why I am just to give one feel what exactly this voice disorder is. This voice disorder, when we produce the voice sound, our vocal tract should be vibrate. And when we produce unvoiced sound, for example, sa, ka, those sound, then our vocal fold should be open. Then, but this vibration has some pattern. Okay, when we produce this a sound or e, u, na, those kind of sound, this vibration should have some pattern, and it should not have any deviations actually. But some of the problem happen when, for example, you have some if some person have the paralysis due to some problem and due to some stroke or different kind of thing, or neuromotor disorder, or some kind of cyst or different kind of maybe problem happen in the vocal tract. So at that time, what kind of sound will occur? So this is a normal you can listen here. So this is kind of prickiness is appearing in the voice of that person. And this is the person with cyst, and this is the person with some. You can see that when we listen this, it has there is no modulation in that voice. Actually, it is steady. But when you listen this one, there is a different modulation is happening in that voice actually, in that R phonation. So that means what? That person is changing that voice characteristic, that vocal fold vibration, as well as that prosody also. That means the modulation of the speech. And then all the evaluation of the speech is important to overcome the after surgery and outcome of the surgery. We need the how we should evaluate the speech of the cleft lip and palate.
Hello. Cecile. Hello. Cecile. Dear participants, sorry for interruptions due to the internet issues. Our experts, uh, Dr. Cecile. Dr. Cecile,
Hello, sir.
what is the issue from there, from your side?
Okay, now it is okay, sir.
Yeah, your voice is okay. Kindly share the your PPT.
Okay, sir. Now, sir, is it fine?
Yeah, it is fine.
Now it's fine. Okay, sir. Sorry, actually, like,
Yeah, no issue. Kindly share the PPT.
okay. So till how much I have covered, like how much is well audible?
Yeah, it is audible. Now it is fine. Absolutely fine.
Okay. So this speech disorder in cleft lip and palate speech I have talked about. Yeah, it's done. Okay. Okay, sir. Thank you. So in phonetics, hypernasalization occurs in the while producing the sound while the phlegm is lowered. So in speech, while producing the nasal sound, our phlegm is lowered, and we produce the sound success ma, na, na, and acoustic energy will come through the nasal cavity. And if vowels are adjacent to the nasal sound, for example, this mama, nana, nan, so at that time this vowel got nasalization due to the co-articulation effect, since that vowel is present near to the nasal sound. So, but this is the normal case when vowel is nasalized, when vowel is in between the two consonants, nasal consonants, that is normal. And but what happened in case of hypernasalization? So, since we have listened some of the audio where we found that this excessive nasality is occurring while producing the oral sounds. So this is called a hypernasality. So in hypernasality, abnormal resonance occurs due to the coupling of oral and nasal cavities. in the production of the oral sounds. So while producing the nasal sound, it is okay, but while producing the oral sound, if this kind of excessive nasality occurs, so this is not good. Then, but with mild hypernasality, the effect is less notable sometimes. Maybe we may not be perceived, that speech language pathologists may perceive that. However, in case of severe hypernasality, nasal consonants replace obstruents. So this obstruents means what happens? This stops consonants, fricatives, and affricates. Those all the sounds replaced by the nasal consonants, and it severely degrades the intelligibility of the that speakers. Then the cause of as I mentioned, the hypernasality is due to the abnormal oral and nasal cavity. However, to get a better idea about this cause, we have to first look into how human speech production system works, and that we'll discuss in the next video. Next slide. So this is the figure of human speech production system. Here actually are two parts. If we see, if we think from the point of view of the signal processing, one is the source, and here this is the system. This acoustic energy will excite coming from the source. It will excite the focal tract, and we'll get the sounds depending on the configuration in the focal tract. This is very synchronized. That everything, all the articulators will synchronously place, and we get the sounds. Here, in case of focal tract, since we will talk about the hypernasality, we have to more discuss, give more emphasis on the focal tract, how it works. So there are two cavities. One is the nasal cavity, and one is the oral cavity. Okay. So while speaking, the air coming through the lungs, through the glottis. That means glottis means the area between the two focal folds, and that letting excite the that acoustic energy excite the focal tract, and we got different sounds. There are generally two types of sounds. One is voice sounds, and another is the unvoiced sounds. So in case of voice sound, the focal folds will not vibrate. Will vibrate, but in case of unvoiced sound, the focal folds will be open. So voice sounds are a, e, u, or maybe na, nga. Those are voice sounds, and sa, ja, kha, then ka, pa. Those are unvoiced sounds. Now we have to know what is the task of this soft palate or this phlegm part. So in case of cleft lip and palate speech, this phlegm act as a very important role here. So when we produce this nasal sound, this phlegm will not connect to this wall. This is called postpharyngeal wall, and airflow will coming through the nasal cavity. While producing the oral sounds such as ta, e, or those kind of sounds, there should be some constriction in that, and airflow should only come through the oral cavity. So this is the idea. So now coming to the problems, what happens really due to which we got the hypernasal speech. So this problem is called the pharopharyngeal dysfunction. So what pharopharyngeal dysfunction? This is the improper closing of the pharopharyngeal valve. So pharopharyngeal valve means our soft palate. So it can't properly close the gap which is required while producing the oral sounds, the vowel. And another problem is called the oronasal fistula. This oronasal fistula is a residual of the surgery. When we need to have the surgery of that cleft palate children, we have to stitch that pellet, and we get some slash from that pellet sometimes. So due to that, some kinds of hole may sometimes appear. So this is called the oronasal fistula. So due to which acoustic energy will couple to the oronasal cavity will couple, and we got the hypernasal speech. Then what are the clinical assessment is there? So there are different kind of clinical assessment is there, which is one is kind of nasoendoscopy. We can see what is the gap size of the pharyngeal gap size. And then another very widely used instrument is the nasometer instrument. So there are two microphones are there. One is nasal microphones and one is oral microphones. And we get the acoustic energy and we get the ratio of that two. And we get one value called nasal score. So that is widely used. And another is called is the imaging technique. We can see the X-ray videos and we can estimate what is the pharyngeal gap size. And another is that perceptual evaluation. That speech language pathologists will ask some of the stimuli and will interact with the children and get to know what is the hypernasal level of that person of that particular children. But the issue is that since these are actually this perceptual evaluation is the gold standard. This is a clinician standard thing. But the problem is that all these things requires a very expert knowledge in all these domains. And perceptual evaluation is biased and subjective, and it depends on the mood of that particular speech language pathologist and knowledge, and whether that person is familiar with that cleft palate children. So all those things will come into picture. And then another thing is that this is a very time-consuming process. If in a society, like if number of cleft palate children is more and this speech language pathologist is very less, it will be a very difficult situation there. And all those techniques is a clinic-centric evaluation. You have to go to a clinic and you need to do a evaluation. So now coming to the rise of this speech signal processing or ML-based methods. So, but what are the steps are there? How we should proceed in that ML-based approach? So, first thing is that we need to identify some of the acoustic cues, and we need to get some of the features. Then we have to model those using ML techniques. These are the very basic steps how to build a machine learning model. Then whatever the model we develop, we have to maybe deploy in some of the web server or maybe standalone application we can develop, and then we can diagnose their speech. And what are the easiest advantage of this thing? These are all are invasive, and then fast, and those are objective. This perceptual evaluation is a subjective method, and these are very comfortable. You can see here this nasometer is not comfortable. Actually, we have found that while doing that kind of data collection, that involvement is required from the children's side. Then it is not biased and cheaper also. And one important thing is that while doing the evaluation, that objective method, the signal processing based or ML based method, can help that speech language pathologist to get better understanding of the problem. Then, but what are the requirements? So once we want to do some kind of project related to this pathological speech model development, so first thing is that we should have one good collaboration with the clinical expert. That is more important. Okay. So then is the database development. So first thing is that unless and until we don't have any kind of good collaboration of that clinical expert, it may be a difficult situation for us to do this kind of research. Then first thing is that since we have spent almost 1.5 years in the database development, and we learn a lot actually in case of database development, and especially in case of speech language pathologists, we should give more emphasis on this database development side, because once you listen those children, then only you will get the idea actually how you should involve. And when we interact with that speech language pathologist, then you will know then how we should develop the model and what are the things we should require from them and what we should we should deliver them. So those are the things are there. So first thing to develop the database is that stimuli design. How we have to design the stimuli. Then we need to do the record of the speech samples, whatever we design. Then we need to do some kind of post-processing of the recorded speech signal. Then we need to recruit the speech language pathologist for evaluation. Since we can't do those kind of evaluation, we have to take help from them. Then once we done with that evaluation, we need to check the whether those ground truth, whatever the evaluation is done by a speech language pathologist, or maybe 3-4 speech language pathologists, whether those ground truths are okay or not. So that also we need to check. Now coming to the stimuli design. So this stimuli design depends on the what type of speech disorder we are going to work. So that it will highly depend on that. Now different kind of stimuli we may have. For example, this phonation, then maybe word level or sentence level stimuli or conversational speech. Then for phonation means sustained phonation, like when we produce a kind of sound, this is the phonation. There is no other kind of consonants will be there. Then this phonation is required for hypernasality evaluation and voice disorder, especially. When we want to do the voice disorder evaluation, we will be needed this kind of phonation. And then different kind of phonation, maybe a, e, u, or different kind of vowels maybe you can take. Then but it is required that you should have this short vowel, long vowel, all those kind of category. And also we need to check what are the vowels is there in that particular language. Then we can have the word level stimuli. So in case of word level stimuli, there may be nonsense word or maybe like meaningful word. So this kind of word like CVCV category you can take, or VCV category. CVCV, for example, papa, pipi, pupu, this kind of things, with different vowels we have to take consider, like all the consonants. For example, this stop consonant, fricatives, then nasals, then affricates, all the consonants we need to taken care. And along with we need to give the vowels like pa, p, or pu, like that. Then VCV also we can consider. Then the different kind of meaningful words also we can consider here. Then coming to the sentence level. So while doing the especially for the intelligibility evaluation or hypernasality evaluation or articulation problem evaluation, we need to have this sentence based study, sentence based stimuli. So there may be different kind of sentences actually. First thing is that oral sentences. In oral sentences, all means most of the, like maybe 90% of the sounds should be oral, like vowels, stops, fricatives. There should not be any nasal consonant. There may be one or two, but not more. Then coming to the nasal sentences. So these nasal sentences which are rich in consonants, or all the nasal consonants or nasalized vowel. For example, this manu, nane, nu, norida. So this is a Kannada sentence now also. Then navina, manendu, vandanu. So these are the nasal sentences. Then another kind of sentences is also there, which is called the oronasal sentences. That means in the sum of the maybe 50% of the sounds are for this oral and 50% of the sounds may be nasal. So this kind of things you have to take care. Then coming to the conversational speech. So why actually we require conversational speech? To get overall idea of what the intelligibility is and what is the articulation score, or maybe overall hypernasality. Or we need to, if we want to check some other kind of speech disorder, for example, prosodic problem, then also we need this conversational speech actually. And at that time, speech language pathologists will interact with the children. They may ask children to read some of the not read actually, ask some to say some of the story or any kind of interaction that speech language pathologists may have. So now coming to the how actually we should record the speech samples. So now this also, it actually depends on the what application, end application you are going to have. For example, if your end application is a standalone device, maybe a software which will be there in your clinic, at that time maybe we can record the sound in a very soundproof room. Or if our end application is a web app, or maybe that voice over IP, those kind of call will come. At that time, maybe we can call through this Skype or maybe other Zoom kind of, or Google Meet, this kind of platform we can use to record the sounds, or maybe in the telephone channel also. Then our data, as I mentioned, we collected from this ICE Mysuru. Then we consider the 44, since we have used that our end goal is to deliver a product or a prototype for the speech language pathologist for All India Institute of Speech and Hearing. So we use this clean room condition, and then 44 kilohertz and 16-bit resolution on monochannel we use. And another important thing is that, for example, one stimulus is there, like Taka. You have to take multiple repetition of that particular stimulus, maybe 10 times or like that. Then in our case, what we consider is that all the children with cleft have undergone primary surgery. Primary surgery is done, as I mentioned, it should be done in 1 year, specially, and do not have other kind of congenital disorder, maybe hearing problem, or maybe some neuromotor disorder, or other some kind of development disorder, or autism, or other kind of things. Then cleft lip and palate children actually has that adequate language ability, so there is not any kind of language problem is there, whatever the cleft lip and palate individuals we have considered. And here, as I mentioned, this all children with cleft palate have undergone, or they don't have other kind of problem. If we want to work on dysarthria, for example, then we have to taken care that only dysarthria is present, no other like stroke or stroke kind of problem, or cleft lip and palate problem, or language disorder. There should not be different kind of. Otherwise, we can't get a very conclusion we can get. This is the important. Then coming to how we need to do the speech evaluation. Then in case of speech evaluation, we have to do the using the clinical expertise is required. Then it depends on the what are the speech disorder we are going to work, and what are the particular task is there. Then it may be we have to take in the subjective, maybe that we can have some kind of rating scale or transcription. Then instrumental based evaluation, this nasometer ratings we can have, and we can have the X-rays to measure the pharopharyngeal gap size. So in this subjective kind of thing, like for example, if we want to do intelligibility, or if especially I am talking about intelligibility or articulation problem evaluation, at that time we have this rating scale, maybe some 0 to 3, or transcription that speech language pathologist will write what are the transcription, like one children's speech, give the speech, and that person will write the what that exactly it is saying. For example, like it is a ASR kind of thing. So that will be the ground truth for our work. Then for this X-ray to measure the pharopharyngeal gap size, if you want to do some kind of computer vision work, maybe you can have that one. And another thing is that from speech, can we estimate the pharopharyngeal gap size? That is also maybe another work. Now, how we evaluate the hypernasality? So speech language pathologists, which have very maybe 5 to 10 years of experience, actually we recruited for the evaluation of the hypernasality. And speech language pathologists provide hypernasality rating in the scale of 0 to 3. So 0 means normal, and 3 means severe. So I'll play some of the sound. No, whether it will be okay, it's okay. Then another thing is that whatever the speech language pathologist will evaluate, they should use the same computer to listen to the samples. Though this is important, because depending on the microphone settings and depending on the computer, that sound characteristics may different. So that's why it is so that it's not biased. That's why we have to use same computer setup to listen all the files. And before giving the judgment, that speech language pathologist can listen the files as many times as he or she wants. Then the order of the samples should present for the evaluation should be randomized. Otherwise, at that time also it will be get biased. So those are the considerations we have to take into account. Then how once we get that ground truth, like that perceptual evaluation rating, for example, then how we validate that whether those ratings are good or not for our work. Because if our ground truth will not be good, our models because we are going to predict those ground truth. If those are not good, then how we can predict that those models, and how we build our models. That is the more important thing. So that's why we have to take at least more than 4 or 5 letters. Like it is suggested that if you have 10 letters or 15 letters, sometimes people take actually, so it will be more beneficial in that case. So after that, once we get, for example, we have 3 letters. So what we need to calculate is that inter-letter reliability. Like for example, one letter, whatever the scores they have given, and another letter 1 and letter 2, what is the correlation? This correlation should be very high. Then only we can take. And then we need to take the intra-letter reliability. So inter-letter reliability means that same speech language pathologist, he evaluate today, and maybe you can give 1 week time, and then he can evaluate after, he or she can evaluate after 1 week. And then what is the agreement, like what is the first day whatever he have evaluated, and what is the ratings, is there any different? So that also it should be in the some range. So for this kind of correlation, we generally use Pearson correlation coefficients if we have 2 letters. If we have multi-letters, then we can use this place kappa for multi-letter agreement. Now, this is where actually we present the stimuli to the speech language pathologists. We develop this UI actually in IIT Guwahati. So this way actually maybe you can give like Kazu, you can give the figure also, then this word also, because if sometimes if people can't read, then this should be there, and you can just, whether it is Hindi or English. So this kind of UI can be developed for that. Then after that data recording, there is coming to the data cleaning, because there will be data will be lots of noise or lots of different kind of situation may be there, and we have to clean actually, we have to cut everything, and those works actually manual, because we don't have any other way to do that. So those cleanings we need to do manually only. And then after that we need to segment, because for example we want to do hypernasality, so we no need the stop consonant or fricatives, we only need the voice portion, because hypernasality is affected in the for oral sounds only. So we have to segment that, for example. Then we use Prat or this wave surfer also we can use. This is one example how we can segment the each sound in a Prat. So this is a manual task. So we have to do all the things in a manual work. Then another task is that maybe we can do using the automatic way. Force alignment we can do force alignment for phone level, phone wise segmentation, or maybe word level segmentation also we can do. In Kaldi it is very easy actually. If we want, we can do that using Kaldi also. And maybe for English we can use this Montreal force aligner also for that this kind of task. Now, coming to the what are the acoustic cues are there in case of hypernasality? Before that, do you have any question, or maybe before I proceed?
Hello, Dr. Sudev.
Yes, sir.
The question, the participant are attending in YouTube. The question will be copy pasted later on your chat box.
Okay, sir.
You may continue. You may continue up to 11:25. Last 5 minutes will be for question answer. We'll give the question on your chat. Okay.
Okay. Thank you, sir. Thank you. Okay. Thank you. Yeah. So. What are the acoustic cues for the hypernasality? Maybe. So first thing is that we should know what is the formats actually. So all us, if somebody actually don't know that, maybe I'll just speak first thing, that one. This is the speech signal, and we, as we know, the speech we process using the short-term processing. Then for each frame, we will have one kind of one Fourier transform. Then we take the magnitude. Then for this higher values, we give some kind of color, and for the lower value, we give some different color, and we make that 3D to a 2D kind of picture. So this is called a spectrogram. So using spectrogram, we can visualize the formats if our window size is small, and if our window size is more, then we can visualize the harmonic structure. So here you can see this is the formant structure for a normal speaker Tata, and this is a CLP speaker which have the hypernasal problem. Here we can see this these red colors, these red color lines. These are called the formants actually. So you can see this for the normal speaker, since this is a Tata, these formant transitions are happening here. Formant transitions is in the onset of the vowel and offset of the vowel, even for this also. So these are the co-articulatory effect. But what you see, what we can see here is that due to this hypernasality, this actually this all the formants kind of come together, and we didn't see any formants which are more perfect here. So, and we can't able to see any kind of formant transition. That means this this is a ta actually. So all are replaced by different sounds, and here all severe hypernasality occurs. Then what are the general acoustic cues for the hypernasality is there? So people generally great researchers such as Gunnar Fromm, then Ken Steven, they did extensive research work for carrying out how what is the cues for the nasality. So later those cues only used by the speech language pathologists to evaluate the hypernasal speech. So they manually check actually whether those kind of cues are present or not in a particular speech utterance, and then they will confirm whether the hypernasal is there or not, for example. Then these are the some cues. For example, the amplitude of F0 is reduced, then increment of this bandwidth, then upward shift of the this fast formant. Maybe I'll just show you. First thing is that these are called formants. So this is first formant, second formant, third formant. Maybe you'll get fourth formant also. So these are called formants. So this fast formant shifting is there. Then changes in the location and the amplitude for F2 and F3. This fast formant and second formant and third formant. Overall vowel quality will reduce. Then flattening will occur in the spectrum. And another thing is that it some energy occurs in the lower frequency region as well as the some mid frequency region that we can see here. So this is one LP spectrum for the different three categories of the hypernasality. One is for the this is normal, then mild, and another is a moderate and severe. So this moderate and severe we clubbed into one category only. So we can see some of the this is the green one is the normal case, and this red and blue one is the more severe and mild. Then you can see here in the lower frequency region some additional formants is occurring even for here also, and for E sound we saw some of the some additional formants occur in that mid frequency region. Even for this we can see here this two formant, this for U first formant and second formant, this come together in got one formant only in case of moderate to severe case. So those are the cues actually. So but the issue is that to identify those cues in again to check using the Pratt or any other kind of software, this is not a good way to look into maybe. So that's why can we model those things? So now coming to the modeling of the hypernasal speech. So for that modeling purpose, we can have the machine learning based approach. So this is a basic structure for a machine learning based approach. So first thing is a speech signal. We can give the speech signal, then feature extraction we can do. Then we can have the database plus and along with the clinical levels. Then we may have some kind of classifier or regression. So we can have the classifier if we need to have some kind of classification problem. For example, we can have that hypernasal versus non-hypernasal, maybe normal speech. But we may need to have some kind of regression if we want to predict the continuous score. For example, if we want to give some continuous score, then we can have this regression kind of thing we can use. Or for example, if we have different kind of variables, like if you have 4 variables, and if we want to predict one variable which is continuous, at that time we can use this regression kind of thing. So here maybe 2 kind of problems may have. One is normal versus hypernasal, and another is the severity level normal, mild, moderate, and severe. Okay. So now coming to the feature extraction, so there are actually different kind of feature extraction process was there for the hypernasal speech analysis, and first work is done in the 1996 that using the Tegar energy apparatus. This is a using that he got some research work done. After that, in 2006, this voice low tone to high tone ratio, this is widely used in even in the clinical side also, people use. After that, one of our Indian researchers, she did in that in IIT Madras, based on the group delay based spectrum, one feature is extracted, and that feature is used for the hypernasality evaluation. Then in 2009, that Mayer, he developed one system actually. Even we can now also we can get that web app for that particular application, and he used this MFCC along with that hidden Markov model based framework. Then this energy distribution ratio, which developed by this Lee in 2014. Then coming to our work, we actually one of our friend, he did lots of works actually in the in case of feature developing different features for hypernasal speech. So maybe if you are interested, you can go through his Google Scholar link. You will get those idea. Then he developed actually the sinusoidal model with some kind of features. Then and we have shown actually how this LP residual is affected while producing the hypernasal speech. So those kind of things we have actually we did in our work. But I'm not going to talk about this feature extraction process. I am more concentrated on the modeling part actually, like how we can model. Maybe we can have only MFCC, and maybe we can have other kind of LFCC or different kind of features. But we are more interested on the product system development point of view. Now there may be two conditions. First thing is that, as I mentioned, hypernasal versus normal speech condition, and another is that predicting the scores. So I'll talk about two exploration, whatever we did. First thing is that combining the vowels to predict the hypernasality. So what happened earlier, whatever the works people have done, what they did, they take the one vowel, for example, a, and they develop some kind of method to give the hypernasal score. Generally, most of the works are hypernasal versus normal, that binary classification. But thing is that when we check that hypernasal scores for different vowels, for example, a, e, and u, and those scores are different actually, and we will get different kind of results for these different vowels. So why not we combine all those? Because we need to develop one system for the speech language pathologists. What they can do, they can give all the vowels and get one score only. So whether we can do that way or not. Then we'll talk about one exploration what we did, very novel work actually, that we took motivation from the clinical domain and try to explore that while predicting the hypernasality for the clinical expert. Now, combining the vowel to predict hypernasality. Now, what we found is that this vowel, as we mentioned earlier, this vowels F0, F1, F2, and F3, those are actually how it will interact if we combine all the vowels. Then we check using a vowel space area. This vowel space area is a very well known in the linguist domain. So we take that one and we check how for different condition like normal, mild, moderate to severe group, in case of phonation and different contexts like ka, ta, pa, papa, tata, or kaka, this kind of context we have checked. And what we found is that before that, maybe I can just show you what the vowel triangle is. So here, this x-axis is the formant for first formant. Then this y-axis is the second formant. So we need to place the coordinate. This coordinate is the F1, F2, F1, F2. Like for this one, maybe for A, E, and U. This one is for the U. Then when we plot this thing, then what we found is that for hypernasal, as the severity increases, then this vowel space area got decreases. So this is a very good observation we have found in case of hypernasal speech. So now when we plot, this is for a maybe one or this may be some 5 speakers data we have taken and we combine, we take the mean. And then when we check for this vowel space area, like if we compute the area under this triangle, then what we found is that this is for pa condition, like papa condition, this tata, this kaka, and phonation condition. What we found is that there is a decreasing trend we have observed. Like this is from the normal to very severe condition, we get the decreasing trend in the vowel space area. So this is a very important use. Maybe speech language specialists can check whether this vowel space area is decreasing or not. Then we can have one kind of use. And after motivating, getting motivation from this work, next what we tried, why not we can combine all the features. Like for example, we have 3 vowels. If in our example, for example, we have 3 vowels, a, e, and u. Then what we can do, we can compute the features for all the vowels, for each vowel for a particular speaker. Then combine, then do the concatenation of the each vowel, and then we can do some kind of dimensionality reduction, maybe PCA or kind of dimensional reduction we can do, and we can add the vowel space area feature along with that. Then this feature vector will get one very long feature vector, and if we model using that machine learning model, actually it outperform most of the works. So and one important thing is that if we want to develop some kind of model or some kind of system, we can give those 3 vowels or maybe 4 vowels or maybe 5 vowels to that system, and it will automatically calculate and it will give one score for all the vowels, and then it will be beneficial for the cleft-lip Pellet space. So I am giving the basic idea. Maybe if you are interested, you can go through this research paper published in that JASA. Okay. Now this is another approach we have, which we have proposed, which is called the grading of hypernasality. So what we found is that whatever the most of the work people have done, those are related to the binary classification. That means whether hypernasal exists or not in that particular speech. But speech language pathologists more concentrate on the grading of the hypernasality, like whether it is severe or mild or moderate. And it will be more beneficial if we can give some kind of continuous scale. And the speech language pathologists can do can bifurcate those. Maybe they can take that the 0 to 0.5 as a mild or more normal, maybe 0.25 to 0.5 as a mild, like that they can segregate that one. So now we develop one model which are mimicking the functionality of the nasometer device. So what we found is that while this is a bar diagram, in the x-axis hypernasality severity level, mild, normal, mild, and moderate, and we asked the children to produce the oral sound and nasal sound, both the sentences. And speech language pathologists help actually in that work also. And then we calculate the nasalian score. So nasalian score means as I earlier shown that nasometer, it have one oral, one nasal microphone and one oral microphone, and then the oral acoustic energy or nasal acoustic energy will divided by the oral acoustic energy plus nasal acoustic energy. So that this is called the nasalian score. So when we compute the nasalian score, what we found is that for the normal speaker, of oral sentences, this nasalian score is very less actually. And then if we see for the moderate to severe speaker, this nasal sentences has the severe, very high score, very high score here. So if we see this bar diagram, what we found is that these normal speakers speaking oral sentences has very low nasality, and moderate to severe speaker speaking nasal sentences has the very high nasality. So what we can consider is that we can consider that these oral sentences from normal speaker and moderate to severe speaker nasal sentences as two extreme nasality conditions. Now, can we exploit this idea while building the modeling? So here you can see that this nasal and oral sound gives the maximum and minimum nasal score respectively. Both the categories represent the two opposite case of nasality. So these two cases we can say as the two extremely opposite cases of the nasality. Now, this working principle actually we are mimicking the nasometer instrument. As I mentioned here, this nasal score is represented by the energy of that nasal sensor and nasal sensor plus oral sensor into 100. Now, this speech signal represent two extremely opposite cases of nasality are used to develop the acoustic models. As I mentioned earlier, that oral sentence saying, producing, speaking by the normal speaker, and nasal sentence speaking by the severe to severe speaker, we consider those sentences as to build a model. Then these two extremely cases of nasality, oral sentence of normal speaker and nasal sentence of moderate to severe speakers, which are referred as oral and nasal classes. So from now onwards, we will consider them as the oral and nasal classes. So this we call as the extreme class model. Since we consider two extreme class of nasality, then what are the steps are there? First thing is that speech signal. Then this is the since we need to only process the voice region. That's why we need to have one glottal activity region detection method. Then after the glottal activity region, whatever the speech frames is there, we have to do the feature extraction. So we can do any kind of feature extraction. Just for the purpose, we are only considering the MFCCs to illustrate the model. Then we will have one oral sentence model and one nasal sentence model. If we have GMM, then we will have the nasal sentence model. We will have one GMM. Then nasal sentence model, one GMM will have. Then for testing, what we can do, we can just take the speech signal, same procedure, then compute the posterior from these two models. Then compute the mean. If we have like 100 frames for a particular utterance, we will get 100 posterior values, and then we take the mean of those, and we can give a score into 0 to 1 scale. So as I mentioned, we need pre-processing this for glottal source activity detection, glottal or voice source activity detection method. So any kind of methods we can take actually. That depends, not depends on that model actually. So for GMM, we'll have two models. For example, two GMM. One will have oral model and another is that nasal model. Then what we can do for a particular, like for example, what we need to do to mimic that, we need to compute the posterior from the nasal model for the particular, for the feature factor Fi. So this is a base. Maybe we can compute the directly compute from that using this algorithm. This is the posterior computed for this Fi frame using this formula. And here actually this prior we have taken equal, so to make the life easy. Then the hypernasality score we can, for a particular sentence S0, we can compute as this way. We can just take the mean of this. Now, if we take the DNN approach, at that time, what will happen? In this case, actually, we have taken maybe 3 hidden layers, or any kind of approach you can take. Maybe other different DNN, maybe CNN also you can take. That's up to we only. Then we use the softmax activation function for the output layer. Then the DNN posterior, since this DNN gives the posterior values only, unlike the GMM, so we can directly write this equation there. So we can see here this is the DNA, this one, and we normalize by the two score, nasal and oral case, and then we'll get the score here. Now, if we compare side by side with the nasometer, here you can see this is the nasal model, for example, you can see, and divided by oral plus nasal, and same thing we are mimicking actually in while doing the modeling. So this way actually we can think. Then we can have some kind of illustration. This is the normal speaker, normal speech. Then this is the mild hypernasality speech. Then this is the moderate to severe hypernasal speech. We can see this is the narrowband spectrogram actually. Then these are the scores actually. These are the hypernasal scores, whatever as I discussed earlier, these posterior scores. Then after GA detection, we'll get these scores here. After GA detection, we remove the unvoiced part, and then we get the these scores. And we can see here, this once this hypernasality increases, this scores is increasing actually. Since we are taking the posteriors from the nasal model, it should be this one. If it is more towards the one, that means for severe case, it should be towards the 1. And for normal case or maybe mild case, it should be towards the 0. So this is what we found. Then we can have one demo actually for this purpose, what we developed. I'll just show this demo first. This tool we have developed in the Institute of Speech and Hearing, and in IIT Guwahati collaboration with Speech and Hearing Institute. And this tool actually earlier they use, and now also they are using in that clinical trials, clinical evaluation in the OPD season. And this tool is like as that web surfer we have. And we'll have different kind of, we can record, we can resample, and we can analyze the speech here. So we can see just, we can open the, for example, we'll give one, so we'll load the speech file. Okay. Then we'll just analyze the hypernasality. So now we can see here. Oh, sorry. Okay, so we give the score in the 0 to 9. So whatever this algorithm I discussed, that mimicking the hypernasality, that algorithm is there in the backend actually. So backend of this tool. So we can see this person hypernasality is severe. So we get the score around 0.89, and this speech language pathologist mark this way actually, from 0 to this 0.25 as normal, then 0.5 as mild, according to their health. So according to their thing. So then for moderate to severe, we'll get this score. So this is the UI we have developed for this task. So we can have the selection-based hypernasality checking. For example, we can select this portion of the file, and then we can check the hypernasality, or we can check the hypernasality for all the speech together. So like that, we can get this one. So this we can do the recording also. Thank you. Okay, then okay. So these are some scatter plots. Please ignore this bottom plot. You can see here, the scores are as in the x-axis, these are the these objective scores, and in the y-axis, these are the hypernasality ratings given by the speech language pathologist. We can see as the hypernasality increases, our scores is increasing towards the 1. And these are some box plot also for a different set of database actually. Then these are some results what we have quoted in this particular paper. For GMM with for the Gertel activity with DNN, we got the, for classification also we did actually, like if it is giving 0, we gave some range actually, and then we did that one. Then with respect to perceptual scores, what is the correlation? Pearson's correlation we have completed, and we got 0.82. So these are actually the performance. So now what is the idea is that in that we have in the basic model we integrated in the MFCC. Maybe we can use different kind of features to combine that. And another thing is that different kind of ML techniques also we can integrate for that particular way of doing that, developing the model. Now, summary, what we have discussed is that we discussed the overall cleft lip and palate speech disorder, what is the disorders that exist, and what is the cause for hypernasality, and how we should develop a pathological speech database. I am considering on the hypernasality, but that will be same for all the kinds of different pathology we have. Then what are the acoustic signatures are there, and how we have to do the modeling. Then maybe if some person interested, then maybe you can have some kind of different future direction actually. So these three actually I have listed. First thing is that explain hypernasality. For example, now whatever we are doing, we are computing the features, and as I earlier mentioned, we saw some of the acoustic signals, acoustic cues, that F0 F1 deviation, F2 deviation. But what exactly actually it's happened? So, since nowadays we can learn from the raw speech, can we do some kind of explainability in that hypernasality? So that also maybe some person can carry out. Another thing is that maybe from the computer vision based side, or maybe computer vision or speech signal processing together, is that to study the phalanx movement. Actually, when because this for the hypernasality or maybe articulation problem, this phalanx movement is the more problematic thing is that here. So what is the phalanx movement? How we can estimate that? Because one thing is there which is called a knee angle. So those kind of thing, whether we can estimate using the this computer vision techniques. Then whether we can estimate the phallopharyngeal gap size. So those kind of things we can do using that computer vision techniques. And another thing we can do is the tongue dynamics using ultrasound video, or maybe you can do it in phallopharyngeal using the X-ray or scenoradiography video. So there is some one of my friends, he did some work in that. So maybe you can look into. But there are different works are there regarding the MRI, especially in computer vision thing. Srikant from Southern California. So if you are interested, maybe you can look into that. So this I have two references. Thank you. Before that, maybe I can just show one video actually, which I should show that one. Just maybe 1 minute only. Okay, so I just disconnect the headphone. Here I can see. So this is the scenoradiography video. You can see here when producing this pata pata pata. You can see. See this is the phalanx actually. This is the phalanx, subphalanx and phalanx. So it is connecting to the. This is the posterior pharyngeal wall. So it is connecting actually when producing this top sounds or oral sounds. So this is called actually knee angle. So these things are there. Now I'll play one video, maybe post surgery on the play. See, their contact is not proper actually while producing that. See, that contact is not. It's quite unintelligible actually, that speaker speech. So these kind of things are there. Maybe you can just look into. Okay, thank you, sir.
Thanks a lot, Dr. Sisi, for your nice presentation. And it was very informative, as we have seen some comment on YouTube chat box. There is some questions. One questions. Kindly request you to see your chat box.
Okay.
And if it's possible, kindly reply it.
Okay. My question is about data cleaning. Is this data cleaning used again for data retrieve, which is cleaning previous? My question is about data cleaning. Is this data cleaning used again for data retrieve, which is cleaning previous? No, actually, for data cleaning, what I am going to say is that, once you got the data, for example, you have the conversation data. So in that conversation data, the speech language pathology, the instructor speeches will be also there, and the cleaning and the children's speech will also be there. So at that time, you have to discard that speech from that particular speech language pathologist, and then we have to only process the speech language, only process the children's speech. Then another thing is that this the data cleaning. Another is that your segmentation part is also there. So regarding the data cleaning, and since we will have different kind of words, for example, papa, kaka, titi, so those will be in it together. So what we need to do, we need to segment, we need to cut those things, or otherwise we can level also that way. Maybe using force alignment we can do that way.
Okay, dear participant, I think your question has been answered properly. And once again, thanks a lot, Dr. CC, to present speech processing for real-time applications. And we hope that some of the participant who is working in speech has got some idea from your work, and may someone may work in near future also. And we would like to thank Dr. Sisir to spend to take the pain to present a wide range of your experience. And with this, we hope that we'll get such opportunity in near future also. With this kind word, again, we want to thank you.
Thank you, sir. Thank you so much. Thank you, all of you. It is my great pleasure actually to be part of this great event. Thank you, sir.
Thank you. And dear participant, our next session will be resumed at 11:35 a.m. by Dr. Amit Bharadwaj, IIT Jodhpur. The topic is haptic communication and kinesthetic perceptions. And for time being, there is some tea breaks. This is a virtual tea break. Okay. Otherwise, if there will be no corona, you could have got some tea and some snacks from NIT Church, but this is a virtual workshop. Then kindly take tea break, and your session, stay tuned. Your session will start at 11:35. Okay, thank you.
Good morning, Amit. Hello. Hello, Ram sir. Hello.
स्टार्ट कर लीजिए। हेलो। Hello, good morning to all. Dear participant and dear esteemed speaker, Dr. Amit Bharadwaj, welcome to the program. So, I am Ashraf Hossain, Assistant Professor, Department of Electronics and Communication Engineering, NIT Silchar. It is my pleasure to welcome you to the fourth day of the webinar on recent trends in signal processing and communication 2020. So before starting the session, it is my pleasure to introduce our esteemed speaker. So today, Dr. Amit Bharadwaj, he will talk about the haptics communication and kinesthetic perception. Dr. Amit Bharadwaj received his BTech degree in Electronics and Communication Engineering in 2009 from YMCAIE, Faridabad, Haryana, India, and he obtained his Master of Engineering in ECE in the year 2011 from Delhi College of Engineering, Delhi. He did his PhD from the Department of Electrical Engineering at IIT Bombay in the year 2016. From June 2016 to January 2017, he was a research associate at IIT Bombay. From February 2017 to December 2017, he was an Alexander von Humboldt postdoctoral fellow at the chair of Media Technology, Technical University of Munich, Germany. After that, he joined the Puhan University of Science and Technology, South Korea as a postdoctoral researcher. In September 2019, he joined the Department of Electrical Engineering, IIT Jodhpur, as an assistant professor. He is a co-author of the book Kinesthetic Perception, a Machine Learning Approach, published by Springer. His research interests include haptic modeling and rendering, haptic perception, haptic data communication, signal processing, and applications of machine learning. So with this introduction, now once again I welcome our esteemed speaker, Dr. Amit Bharadwaj. So may I request Dr. Amit Bharadwaj, please start your session.
Yeah, thank you, Ashraf. Am I audible?
Yes, you are audible.
Yeah, thank you. Thanks for the nice words. And I thank Dr. Chandrajit for inviting me. I hope that whatever I will talk today, it will be an benefit for the NIT Seltzer community and the students who are attending. Okay. Let me present my screen.
Yes.
Are you able to see my screen?
It is coming. It is.
Yeah. Yeah. Thank you. I hope it's visible now. Okay.
Oh, it is coming. It is coming.
Okay. Uh, Today's talk, title of today's talk is Perceptually Adaptive Sampling for Haptic Data Compression. As I interacted with Dr. Chandrajit, he mentioned that the conference or the workshop is on recent trends in signal processing. Then I chose this topic that it should be apt for this conference, and that's why it's perceptually adaptive sampling for haptic data compression. Yeah. Now there are it might be some new thing for the audience. What is haptics? I will spend 10 to 15 minutes on haptics, and then we will take the topic as it is, right? Yeah. We as human beings have five senses, right? Audio, we can listen, we can visualize, it means we can have a sense of taste. We also have taste of smell, and another sense we have sense of touch, that we can feel the object, whether it's hard, whether it is soft. This kind of sense we called it sense of touch. And for a long time, all other senses, mainly audio and video, has been explored a lot, but touch has been unexplored for a long time. Now, in general sense, what is haptics? Haptics, the word ha- haptic has been originated from Greek word hapticia, and its meaning is to touch. Okay, then haptics means the study of science of touch, the study of sense of touch. And in this study, mainly in haptics, we try to explore or understand our human touch sensory mechanism and our motor characteristics, how we perceive the things. And on top of this, we want to we want to develop a computer controlled system that allows us to physically interact with various environments through touch. And these environments can be virtual environment or remote controlled. Okay, it means we want to provide the sense of touch that we feel in the real world. We want to make it in virtual world also, and we want to touch the remote object. For example, if my friend Chandrajit is sitting there, and I want to shake hand with him remotely, then how can I do? Then it means I mean to say this thing, that we want to develop a system with which we can physically interact with a remote environment. Okay, that is also the goal of haptics that we want to study in the years to come. This is the brief history of haptics. As I mentioned in my first or second slide, that it has not been explored for a long time. The word haptic was used in early 20th century by psychologists. Okay? I mean, they were using for in their psychology study or perceptual studies. But around 1950s, there was research going on in the field of robotics, and then people started using force feedback for teleoperation kind of application. It means when you try to touch an object by a robot, then people thought that why can't we give back the sense of touch or the force feedback to the remote operator. Okay, during that time, this force feedback was very popular for 30 40 years in robotics domain. And since then, this this area, it means applying force feedback, started I mean, people started working in this domain from 1980s to 1995, mainly University of Stanford and MIT. Two people are very well known in during that time. Professor Salisbury and Professor Mandayam Srinivasan, and one is Indian. And they did pioneer research in this field, and they contributed a lot for haptics, and from there many researchers have taken forward. Yeah, in as I mentioned in 19, the same group was working the on haptics research, and in 1995 they came up with a new haptic device, Phantom, and that was a big breakthrough. And till now, Phantom is very popular, the Phantom series, and more than 10 around 10,000 research papers have been published, or I think around 10,000 paper have been published using Phantom device. And after 1995 to till 2000, this actually till 1995 or till 2000, haptics research was only limited to United States of America. Then it started moving outside. Then it started moving. It started growing in USA also, as well as in Asia, Japan and Korea. Why Japan and Korea? Because at that time, in the two labs, Stanford lab and MIT lab, most of the students were either Japanese or Korean, and then they took this research to their native countries. And after that, Europeans started doing research, and since then, now it has gained momentum. Now, what about India? India, we don't have much presence, but two or three labs they are doing very well. One at IIT Madras, Professor Mani Vannan from Department of Biomechanics. He does very good work in haptics. Another lab from where we Dr. Chandrajit and I have done PhD under Professor Subhashish Chaudhary. He does have research in the domain of haptics. Yeah, only two well-known persons, and now I'm trying. Just now I joined. I'm trying my best to start haptic research in India. Yeah. Now you know that haptics is a sense of touch. Okay. Now what kind of sensations we have? Now, as this figure tells you that it means this lady has put her hand on the grass, then what kind of sensation you can feel? You can feel it's soft. Grass is very soft, and you may feel some pressure. Now, this kind of sensation you feel through your skin, okay, and it means the mechanoreceptors under your skin are responsible for perception of hardness, roughness, temperature, pain, and yeah, friction. All these things comes under your tactile sensation. Okay. Another sensation is called kinesthetic sensation. Kinesthetic sensation, I should start by this way that without kinesthetic sensation, you can't move your hand to the desired position. It means kinesthetic sensation tells you the relative position of our body parts with respect with each other. If it means if you lose your kinesthetic sensation or proprioceptive sensation, then you even it means in the figure shown here, the person is want to lift his hand, and visually he can see that uh, he want to lift this hand to a particular position. But if you don't have the kinesthetic sense, then you can't do. Then kinesthetic sense is very much responsible for our movement of our body parts. Okay, and it means without kinesthetic sensation, you even can't walk because you don't know where to put your leg forward, right? Then haptic sensation is a combination of tactile plus kinesthetic information. Why? It means in your daily life, you perceive the things through both the sensation. For example, if you want to lift a cup of tea, then you should move your hand, or you should lift the cup, and when you lift the cup you feel the texture of the cup. It means the your tactile sensation as well as your movement parts of your body, your hand with respect to the cup position are taking place. It means you are responsible for that event. Okay, then it means the haptic sensation is a combination of tactile plus kinesthetic information. My voice is audible, right?
Yes, yes, audible. It is audible.
Okay, thank you very much. Yeah. Now, uh, now we have discussed what are the areas, what are the sensations in haptics. Now, since it's a we are in the domain of research and we are academician, we would be interested in knowing what are the possible research areas in haptics. It means where can we contribute? There are three main domains. It means haptics research is divided in three parts: human haptics, machine haptics, and computer haptics. All these three domains are very much interrelated to each other. As I mentioned in my first slide, that the domain of haptics, we want to understand our human sensation. We want to understand our human capabilities of perception. It means what is the minimum threshold we can perceive? What is the minimum amount of force we can perceive? What is the just noticeable difference of a human being? Okay. All these things are studied in human haptics, the perception. Another thing is that we want to design some haptic interface, which can I will explain later what a haptic interface. We want to design some haptic machine, and that consists of some sensors and actuators, and it means the characteristics of a machine or the specifications of machines will be governed by our human sensations. Okay, it means how, what are the human capabilities we should, it means have all these, whatever we will design, that is very much related to the research done in human haptics. Another domain, computer haptics. As the next point I mentioned in the very first slide, that we want to develop a system to interact with virtual environment. It means now another domain uh, is haptic rendering. Now you want to touch a virtual object, and now what are the issues related to that? How to touch that virtual object? Now getting force feedback from the virtual object, and how to make this whole system stable. All these things comes under computer haptics. Hence, haptics research is very interdisciplinary, as mechanical, robotics, or control persons may take research in the domain of human haptics, in machine haptics, electrical, computer science, people, even people are doing research in computer haptics, and cognitive psychology and neurophysiology, biologist person can work in human haptics. Now it's a complete uh, chain, and it's very interdisciplinary research, and anybody who has the expertise in these domains can take this research forward. Yeah. Now, uh, haptic interaction in virtual environment. How does it take place? What do we need to make this happen? Now you see this figure, that one side is human, and another is machine. Okay. Now there is a human hand. Human hand is holding a and effector. And effector means and effector of a device. Okay, we need a device, and the device had some sensors. Now have human hand, with the help of and effector, moves the stylus of haptic device inside the virtual environment, and whenever the virtual environment is touched by the haptic device, and there is a collision between these two objects, then then a force rendering algorithm will calculate the force, and that force will be computed, and it will be given back to the human hand with the help of haptic device. And once you Once you feel the haptic, the force, it goes back to your brain, and it acts um, accordingly and acts you to move your hand. It means the whole cycle is complete. It means now uh, you give some force motion commands to the device, based on the virtual environment conditions, whether you have touched the object or not. If you have touched the object, the force will come back and you feel the force through your human sensory mechanism. Okay. And it means the human, this haptic interaction is bidirectional, right? It means bidirectional means you have given force motion commands, and after interaction it comes back to you as force signal, force, or it depends on what kind of haptic sensation you are interacting with. Okay, I hope it's clear. Yeah. Now, for haptics in virtual environment or for remote environment, you need haptic interface to interact with. And there are two types of haptic interfaces, as there are two types of haptic sensations. Uh, One for kinesthetic sensation, you need force feedback haptic device. It's a point contact device, and um, it depends on the type of device, how many degree of freedom. Mainly, it has 3 degree of freedom input, uh, and other kind of device is called tactile interface. This is example of this tactile interface is vibrotactile actuators in your, or actuators may be used in your mobile devices. Yeah, these are some examples of kinesthetic devices. It's just like Phantom 1.5, Phantom Desktop, Omega 3.0, Phantom Omni, Maglev. All these devices are used for different applications depending on what kind of resolution they have in force, what is the maximum force they can provide, what is the workspace. For example, this Phantom 1.5 gives you force up to 10 Newton. Its workspace is a little bit more, but if you compare it with Omega 3.0, its workspace is not that big, but its resolution is very high. It means the resolution is better than Phantom 1.5. Similarly, in maglev, its workspace is very small, but it's better in other senses. Now it means it depends on your application, which kind of haptic device you want to use. Phantom Omni is a little bit cheaper. Other haptic devices are costly. Phantom Omni, you can market cost is around 1.5 lakhs, but other devices will cost us more than 10 to 15 lakhs. Okay, I think Phantom 1.5 cost is around 20 to 25 lakhs. Omega 3.0 cost is around 18 to 19 lakhs. Yeah. Now, quickly, I will go this since we have to discuss something else. What are the applications of haptics? Haptics, one of the application is designing some assistive technology for visually impaired persons. Okay, you can imagine how can we use the sense of touch in helping visually impaired person. Digital museum, um, there might be many good things in Assam that I want to, sitting here in Rajasthan, want to explore and want to feel the sense of the artifacts and some very good monuments in your Silchar also. Then how can we design? It means we can have some digital museum. You can provide sense of touch. So for example, if you want, I want to feel the texture of Taj Mahal, then we can use this technology. It means you just have your virtual environment, and with the help of our virtual these haptic interfaces, I should be able to feel the texture and it means whatever we can be we will be feeling as in the present as a person, we can feel in the virtual environment. In medical training, haptics can be used in medical training in imparting uh, the education to medical doctors. And I hope many of you might have seen this movie uh, by this Munna Bhai MBBS. The one character tells that, okay, bring the body. And if we, it means uh, for medical practitioners to to perform some medical surgery, you need body to act, to perform some action. Now, if you use haptic technology, and you use dummy bodies in a virtual environment, and then you provide sense of touch, and how to cut the bones, and how um, m- to stitch, and all these kind of feeling can be given with the help of haptics. It means can be given. I should say that haptics research is in the very early stage. The goal is that we should be able to give in future uh, that kind of medical training with help of haptics. Okay. Another important application is in gaming industry, that as you know that you can imagine that whatever games we have, and we can have a sense of touch in those games. Another application, telepresence and teleaction. There are many applications in which human can't go, or even if he or she goes, it may be hazardous for him or her. Okay. For example, if you want to operate, or you want to be, if you are working in a nuclear plant, and you will be handling some radioactive element, and that can be dangerous for a human being, then we can use haptics in that kind of teleoperation of kind of application. Or even this teleoperation application can be used for medical purposes, right? Even for example, if uh, some catastrophe happens in Rajasthan, and very good doctor is present in Silchar, then we want to use his expertise, then he or she can perform some medical surgery with the help of robotics, and with the, and along with that, the sense of touch. It means using sense of touch, he will be feeling that he's sitting in Jodhpur, and performing operation as a person. Okay, now in today's talk, we will be focusing only on this application, telepresence and teleaction. It means what is the use of haptics in uh, in teleoperation. Okay, just a minute. Okay, haptics for teleoperation, as I mentioned. Then what a teleoperation means? A teleoperation has a, a operator, a teleoperator. Both are connected by a communication network, and now you want to control a teleoperator. Okay, and what will you do? A operator will send commands to teleoperator. It means it will send position and velocity signals, and receiving these signals, the teleoperator acts. And once there is a action taken by teleoperator, which means there is some collision, the force is computed, and this force is sent back to the operator. Now it means there is a over this whole network, there is a control loop, right? A global control loop. It means one end you are sending position velocity, another end you are getting force or torque. So a loop has been created, and and it means it means if you consider haptics in teleoperation, then it's a bidirectional communication. And both the things are unlike audio video transmission. If you want to transmit haptic over this network, it's a bidirectional communication, right? And there are two types of loop here, local as well as global control loop. Now, what are the issues? It means if you want to transmit haptic signals over this network, over some communication network, and you want to perform some teleoperation, what are the issues? Issues is that, as I mentioned here just now, that haptic signal transmission over a communication network is a bidirectional. Okay, it means you are sending position velocity, and you are getting back the force people. And any kind of there is a control loop, right? Now any delay may cause instability of the global control loop. And another requirement that haptic, for better quality of perception, or for the transparency, the haptic update rate, you should be perceiving, you should be sending 1,000 samples per second. Otherwise, you will not be feeling the real sense of haptics. Yeah, that's the key point here. That for for transparency of sense of touch, the update rate should be 1,000 samples per second, and to maintain that kind of update rate may cause congestion in the network, and that may cause further delay. That it means the only solution is that we should compress haptic data. And how to compress haptic data? May we compress this haptic data by conventional approach, that what the way we did in audio and video? No, we can't do, because this is a all these are block based approach, and these block based approaches use some kind of delay, and any kind of delay may hamper the bidirectional transmission. Okay. Now the only way to compress haptic data is that we should compress the haptic data while maintaining the quality of perception. Then what is the solution? Solution is that we should transmit only perceptually irrelevant data. Okay. And what is the mechanism? One way to design this perceptually adaptive mechanism is based on a very classical law of perception given by Weber's. Weber's tell you that if it means he started his experiment by weight. For example, if I give you on your hand with I ask you to lift 100-gram weight, and then I add 5 gram to it. Okay. Now I ask you, have you perceived any difference? You may say yes or no. If you perceive, for example, if you perceive, then you will say that the just noticeable difference is 5 gram. Okay. Less than that, you will not be able to perceive. Now you think that now I just first I put a weight of 5 gram on your hand, then I just add 1 gram. Then I ask you, can you perceive? Then you will say yes, yes, I can perceive. Then Weber tells you that the perception depends on your own absolute relative differencing, not absolute difference, relative differencing. It means if the absolute relative difference between two stimuli exceeds a particular threshold, then you can perceive that current sample. Okay. For example, in this figure shown here, you are starting from this red sample, and new samples are coming, and once your relative difference exceeds a threshold, your threshold is a human specific, everybody has different threshold, and if the threshold is, let for example, is 10%, if this threshold exceeds by 10%, this absolute relative differencing, then you will be sending this another red point. Then based on now this red point becomes the reference. Then and using this red point, you compute another relative differencing and send this another third point, this third signal, red signal. Now this way you will be sampling. It will this is a non-uniform kind of sampling. And this blue region in which you tell that all these are perceptually insignificant samples, are not transmitted, and these are called perceptually dead zone. Means it's called perceptual dead zone. No need to transmit these signals. Right? This is the mechanism of perceptual adaptive sampling. Yeah. Now in this talk, I will be talking about two main things. Okay. It means solution of transmitting haptic signals for a teleoperation kind of thing is perceptual adaptive sampling mechanism. And one of the way is based on Weber's law. Okay. Now in this talk, I will be talking about possible structure. It means what are the other ways of doing this non-uniform sampling, and what are the factors which affect these perceptually adaptive sampling mechanisms. Fine. Let's start. And the approach we use here is based on machine learning. It's data-driven approach. For that, first we design experiment for recording haptic responses, and we did this for several users. And having recorded the haptic responses, we design or we predict the responses based on some classifiers. It means we predict human haptic response. And our hypothesis for using classification or classifier is that a good classifier may turn out to be a good candidate for adaptive sampling, and that we verify. This is one of the experimental setup that we used in our lab, and this is the haptic device that while I was showing the examples of haptic device, this is the haptic device Phantom Omni that we used. In this experimental setup, I'm explaining here this one experimental setup. Others next time when I will be talking the next experiment, I will just skip that point. In this experimental setup, a user is subjected to a haptic force signal and asked to respond on a perceivable change in the force. Okay, we give a piecewise constant force, and we ask user, did you feel any change in the force? If he or she perceive a difference in the force, then that level is called +1 perceived. Otherwise, it's -1. Yeah. Then we classify. Then it's a feature vector. That force signal is your feature vector, and label we are defining as -1 and 1. -1 means non-perceived difference. 1 is perceived difference. And then we define a performance metric, means the number of the just the average of misclassified point. Okay, and h of xi is your uh, um, is your decision boundary that we will define just now. And to classify, then we have used to verify, we have used holdout cross validation. Yeah, one mechanism to classify is based on Weber's law, that current force x will be perceived if its relative difference with the previous force exceeds a threshold delta. Okay, now in this scatter plot you may see along x-axis is your previous signal, and along y-axis is your current sample. And once you feel the change in, in force, then user press the label it +1. And the +1 signal are shown here by here red square, and all no, sorry, I have mentioned in the other way. Blue dots are perceived, and red points are unperceived, non-perceived. Okay, it means this is the then this region we will call as perceptual dead zone. And this way we have defined this your error matrix for Weber's classifier. Another way we used as just, it means here we are assuming that perception is just absolute differencing. It means once your current sample exceeds the past sample by some threshold C, then you will be able to perceive the difference. Then this way we defined the error matrix, and we computed the error matrix, and for 10 users we showed that level crossings, yeah, this one we will call level crossing. Level crossing means just absolute differencing performs slightly better than Weber classifier. Weber classifier is very well known, but here we told that we verified that for a force up to range of 3 Newton, absolute differencing also works well. Yeah, and we even verified it on a real signal. This is typical haptic signal, and we tried to reduce the haptic data rate using both Weber and level crossing, and it comes out that here also our absolute differencing is quite well as compared to Weber, Weber classifier or Weber sampler. And yeah, and then what is the conclusion? Conclusion is that we are not saying that Weber is not good. We are saying that both Weber and level crossings are good candidates for adaptive sampling. Performance wise, if you want to say, it means level crossing is slightly better. And signal analysis, it means it's level crossing easier because here you just need to take absolute differencing, no relative difference. That's why we say it's quite easy. Yeah. Another topic. Now, one thing we have, I mentioned here that we have uh, identified two structures of perceptual adaptive sampling mechanisms: level crossing and Weber classifier or Weber sampler. Okay. Now, other things that we wanted to talk about here in this talk, the factors affecting perceptual dead zone. Perceptual dead zone means the region in which you don't you say that these samples are perceptually insignificant, no need to transmit. What are the factors? Okay, one is haptic temporal resolution. What is this? For example, this is a kind of signal. This is a kinesthetic signal, force signal you have given to a human user, and you see here that A and B are two jumps, and assume that these jumps are perceivable. Perceivable means they exceed the Weber constant as well as level crossing. Okay? It means the difference is that high that both are beyond perceptual dead zone. Okay, it means both are perceivable. Now another thing, now you want to measure. It means what is the minimum time spacing between these two perceivable jumps so that both are perceived differently. It means if both, it means along y-axis the difference is quite large, but if in along x-axis the difference time, the time sampling is too small, then you just feel only one jump. That was the motivation. For example, the motivation here is another way to define this problem, that one sample, the one which means red samples are perceptually significant ones, and delta t is the difference between two perceptually significant samples. Now we want to say that is there any minimum value of delta t? What should be the minimum value of delta t? And for example, if this delta t, the time difference between two perceptually significant samples given by any of the perceptual adaptive sampling mechanism, whether level crossing or Weber's classifier, is less than temporal resolution, then you will not feel. Temporal resolution means the minimum time spacing required to perceive two jumps different from each other. Then you will not feel this red point, the second red point. Then because this delta t is smaller than this minimum time spacing, then you will be feeling this point, the this sorry, not red point, the just after the black point. This point you will be perceiving. Now it means you should also take care the temporal resolution also while designing or while applying perceptual adaptive sampling mechanism. That was the motivation, and we in our study computed temporal resolution for many users. And as I told you that these are these all these things are perceptually driven, then it varies from person to person. And this temporal resolution for different users, I think it varies from 17 to 37 millisecond. And what is the conclusion? Conclusion is the same thing, that temporal resolution, the minimum time spacing required in perceiving two jumps different from each other, is in the range of 17 to 30 millisecond. And yeah, this thing that we also found out that fatigue, that if you want, you just perform the experiment for a longer duration of time, and then your temporal resolution goes down. It means it affects your temporal resolution by 30%. Another very important thing, that till now we have just studied the difference in two force signals. Okay, difference in two force levels, whether it's absolute difference or relative difference. But what about the direction? Okay, it means what of the direction means now if we want to consider a force signal in 2D or 3D, then what will be the structure of perceptual dead zone? In case of 1D signal, perceptual dead zone was just like a square, right? That I showed here. Just a minute. Yeah, these the blue things. Uh, these are your perceptual dead zone. Okay, just blue region. But in case of the 2D signal or 3D signal, what will the perceptual dead zone? Then these might be the possibilities. This for 2D signal, the dead zone, perceptual dead zone, in which the the force change. If there is any change in the force on 2D force, you will not feel the change. That perceptual dead zone may be circular, may be elliptical. For example, here the reference force is F, this F signal, and around this reference force, if uh, any change is around this circle, then you will say you will not be feeling any change. And similarly for elliptical dead zone, it means we don't know whether this for 2D signal, what is the shape of perceptual dead zone. Then idea was the same that as we did for 1D signal, we recorded haptic responses for several users for 2D signal, and the hypothesis was the same that we will design some classifiers, which one predicts the responses better, that will define the structure of the dead zone. Here we considered uh, um, these kind of structures: Weber, level crossings, elliptical, oriented ellipse. These kind of structures we tried, and we compared their performances, that which one gives you better performance in predicting responses. And this is the scatter plot. Blue dots here tells you that these are the perceived changes, and red means that these are unperceived. And uh, the research, our research tells that uh, there is no much significant difference between circular and elliptical dead zone. But this line of research is still active. Uh, our research tells that there is no effect of direction. But another line of research done by one of my collaborators, they tell that there is effect of direction, but they are also not convergent on that point. But this line of research is still active because, yeah, but till now there is ambiguity. Our line of research tells that there is no directional preference, and level crossings classify performance better. It means level crossing tells what is the structure. Level crossing means absolute difference. Absolute difference means it's a circular dead zone. um, um, till now our research tells that for 2D signal, the perceptual dead zone will be circle, and for 3D it will be just a spherical. Yeah, another factor that may affect perceptual dead zone is the rate of change of signal. It means how fast a signal changes. It means you can't apply the same stick to every signal. If a signal changes very fast, then its threshold for determining the perceptually significant point will be same as compared to that signal which is just slowly varying. Then we did this study, and the motivation came from another study on temperature, and they found out that actually this study is very old study, and did on temperature. It was done around 1968 by Professor Cancelo, and they mentioned that just noticeable difference of temperature decreases as you increase the temperature. It means as you increase the rate of change of temperature, your just noticeable difference goes down. We expected the same kind of thing for kinesthetic signal, that if the rate of change of force signal increases, what will be the effect on Weber constant or level crossing constant. Yeah, we design an experiment, and this was our reference kind of signal we used. We started from a reference force and we varied the slope of that signal S, and we asked users, can you feel the difference for a particular slope? Or it means the slope was random in nature. Slope was uniformly taken from -1 to 1. That was the thing we wanted to measure. That ideally, as you increase, it means red dots are unperceived, blue are perceived. As you increase the slope, your GND is going down. Okay, that we wanted to study. Yeah, then we use the same technique. We applied uh, classifiers, linear and exponential. It means what is the size, shape of the boundary, right? The boundary means the region that separates perceived and non-perceived point. It can be linear or exponential, and based on the error metric, which one gives better performance, that we will stick to that point. Yeah. Then our results tell that as you increase the slope, rate of change of signal, your Weber fraction or your Weber threshold goes down. Yeah, it's quite obvious. That means if the signal is changing very fast, then you changes the. It means you quickly respond, and your threshold, your perceptual threshold goes down. And if the signal is changing very slowly, then you just get adapted to the change. You can't feel the difference whether there is a change. There is a change in the signal, right? That was the observation that we also did, and this is along the same line as that of the temperature study. And and we also found out that this change, that the change is asymmetric. Means it depends whether the rate of change is increase. It means whether the slope is increasing or decreasing. Now, amount of decrement in Weber fraction or Weber constant depends whether the slope is increasing or decreasing. For decreasing slope, the change is much. That means Weber fraction decreases much when the slope is decreasing. It means if, for example, if the force is decreasing, then you quickly get to know that the force has changed. Now, this is the conclusion. Yes, Weber fraction decreases with increase in the slope for both increasing and decreasing force stimuli for most of the users. And yeah, there is asymmetric behavior of perception between increasing and decreasing stimuli. Yeah. Next thing and last thing that we studied, whether kinesthetic perception is a function of task. What do I mean by this? See this thing. If you can see my screen, that your perceptual dead zone is defined by either level crossing or by Weber classifier. If you follow level crossing, then it takes you it asks you to sample the next signal based on absolute differencing. If you consider Weber classifier, that then you did the same thing using relative differencing. Then the type of dead zone you get here, the red is the dead zone given by level crossing, and blue is the dead zone given by Weber classifier. And the reason dead zone means, in this region, if there is any change, you will not be able to feel. Now, there are two lines for each dead zone, upper line and lower line. Upper line corresponds to just noticeable difference 1, GND 1, and lower line corresponds to GND 2. GND 1 means, for example, you are the reference force is 1.5 Newton, and now you want to increase the force, and at what point you will feel the change in the force. For example, if you have felt the change at 10 Newton, at 1.6 Newton, then your GND is 0.1 Newton. Okay, and JND2 means you are starting at 1.5, you try to reduce the force and you feel the difference at 1.4 Newton. Fine. Now that defines your JND1 and JND2. As you might have noticed that in case of Weber and level crossings, structure of perceptual adaptive sampling, we have assumed that JND1 and JND2 are equal. It means if you have felt a difference in force in upward direction at 0.1 change, you will also feel the same at 0.1 below. It means 1.5 is your reference and 1.6 you will feel the difference, 1.4 you will also feel the difference. In between, you will not feel the difference, you will perceive them insignificant. For example, if your reference force is 1.5 Newton and I give you 1.55, you will not feel any change in the force. Okay. Now, next thing is that what if this assumption of having JND1 equals to JND2 is violated? Okay. Then what should we do? Then we should compute just noticeable difference 1 and JND2 separately, and whatever the dead zone will be given, then you can just add these two lines. It means first you compute the just noticeable difference in upward direction, and then once computed, then you compute just noticeable difference in the lower direction, and then once you have computed two lines, then you just add up. It means just plot on the same. Then you have two lines. That will give you the actual perceptual dead zone. Okay. Now we wanted to it. We thought that it might be different, JND1 or JND2, but if it's equal, then our assumption of Weber and level is fine. Then what did we do? Then we took two approach. One is discriminatory approach. In this discriminatory approach, what we did, we asked user to look at both sides of chains and taking care of JND1 and JND2 altogether. Comparative approach, it looks only at one query at a time, increment or decrement, and then we define two dead zones, discriminative dead zone and comparative dead zone, and then we want to compare these two dead zones. Yeah, procedure. It means we need to guess in this perceptual study, we need to compare successive trials. Yeah, we defined three tasks. Task 1, user should respond yes if current stimulus, the force signal, is different from the previous one. Different means it can be higher or it can be lower. Okay. Task 2, respond yes if the current stimulus is larger than the previous one. Okay. That means it's JND1. Task 3, respond yes if the current stimulus is lesser than the previous. It means JND2. Then task 1 corresponds to discriminative study, and task 2 and 3 belongs to comparative study. Okay, then what did we achieve? In task 1, the comparative discriminative approach, that here user was asked to respond whenever you feel any change in the force, then we get this kind of scatter plot in the leftmost figure. And the region below, these are two lines, and the in between region is called perceptual dead zone. Task 2 means user was asked to respond whenever they felt the current stimulus is larger than the previous one. Then this kind of JND1 line we observed. And task 3, user was asked whether they felt the current force smaller than the previous one. Then this kind of line we perceive. It means here in all these figures, red points mean that they are unperceived, they are non-perceived. Okay. It means, for example, here in rightmost figure, task 2, red point, blue points mean your current stimulus is higher than the previous one, and user has responded correctly. It means user has responded that way. And red point means user has considered that that current stimulus is lower than the previous one. Then what are the dead zones? Now, as per the definition, we should add up the dead zone, the lines given by JND1 and JND2. As in case of discriminative approach, both blue lines, it means in one goal you define perceptual dead zone. Then you get to know that for different users, this perceptual dead zone given by discriminatory approach is larger. It means it's wider than the comparative approach. Okay, it means for all the users, this is the main thing that we observed. It means that your kinesthetic perception is a function of task. It depends whether you just want to compare the signals larger or lower, or you want to feel the forces as different from each other. It means whatever the perceptually adaptive sampling measure you want to apply, that's also a function of task. And the reason it's beyond the scope of this talk. The reason why we are getting this kind of thing, I will just mention here that that comes under this. Anytime if I would be giving a talk on perception, that was the reason behind this is sequential effect in perception. If anyone interested, then just may note down. The reason for having two different types of dead zone here for discriminative and comparative approach is sequential effect in haptic perception. Yeah. Conclusion is that the dead zone 1 and dead zone 2 found to be different in terms of width and GND, and it signifies that perceptual dead zone depends on the task. Hence, the dead zone or the perceptual adaptive sampling mechanism should be defined based on the task performed during a teleoperation. Yeah. In summary, what we achieved during our study, that level crossings and Weber sampler are two good candidates for adaptive sampling. There is no directional preference for kinesthetic perception. It means there is no directional effect of directional perceptual dot zone, but still we need to carry it forward to certain to have the valid point on this. Yes, Weber fraction or just noticeable difference depend on rate of change of stimuli, and it decreases as the rate of change of stimuli is increased. And we estimated the minimum time spacing required in perceiving the time difference and the required in perceiving two jumps different from each other. That's temporal resolution, and that should also be taken care while designing perceptual adaptive sampling mechanisms. And at last, we demonstrated that kinesthetic perception is a function of the task. Yeah, that's all from my side. And yeah, thanks. Thank you very much. If there is any question, I will be happy to answer.
Thank you, Dr. Bharadwaj, for your nice presentation. I think participant has some questions.
Yes, yes.
So, no question. So I think participants they have no questions.
Okay.
Actually, your session it is on live in the NIT Silchar YouTube channel.
Okay, that's fine.
In the Google Meet only 5 people are there, but your whole session was live telecast in the YouTube channel of NIT Silchar. So because there is no question, so it is the time to give the thank you to the esteemed speaker, Dr. Bharadwaj. Hope the participants will be benefited by your nice talk on the haptics communication and kinetic perception. So, hope your association with Department of EC, NIT Silchar will be continuing in near future also. Thank you very much.
I will be happy to come. Even my good friend is here, Chandrajit, and once this.
Yes,
Corona
Amit, we
period
will be
over,
very happy to have you here. We can
Yes.
go around in the Northeast, go around for a trip, and our students can always, benefit a lot from you.
Yeah. Even I am looking for student in haptics. If you may also
Yes,
forward.
yes, sure. Yes, yes, yes.
Yeah. Okay.
Thank you
Thank you
for
so much.
attending this. Thank you for sharing your knowledge at such short notice.
Okay.
Thank you
Thank you.
so much, Amit.
Thank you, sir.
Thank you. Thank
Okay.
you.
Thank you, Dr. Ashraf. Thank you.
Yes, sir. Thank you.
Okay. Bye bye.
Bye. So, dear participants, your next session will start at 2:30. So, so be there at 2:30. We will see you at 2:30. Bye.